never touch the sound guy's stuff without asking. Hi, folks. My name is Jeff Otter. I'm with Hewlett Packard Enterprise, and I'm going to give the two updates today for two different work streams. Unfortunately, due to some conflicts and some accidents, he's okay, but neither Sammy nor Daniel are able to attend today. So I'm going to try to cover all of the slides for both the work groups. So you'll probably guess which ones are the ones that I made and the ones that I didn't. So with that, I'm going to cover both the data center efficiency metrics work stream and the power and telemetry work stream. So I'm going to start with the data center efficiency metrics. So this work stream is looking at ways to improve or to further the drive for more power efficiency. As everyone's talked about the carbon footprint of this, obviously the operational, the use phase, the electric consumption is the majority of the IT, carbon production, and so trying to reduce the energy usage overall is the primary goal. But the secondary one, which is probably the one that given the scope and the increase in power consumption goes on, making sure that we're using that power as efficiently as possible and putting as much of that energy towards the actual work itself and not the overhead of running the data center. That's where we're trying to provide metrics that show where that energy is being consumed, and then what can we do to improve that. So the first is that the work stream meets weekly on this, and this is the kind of the scope of that. And let me just get into to what the group is doing. So what's known as PUE. This is not new, but the power utilization effectiveness. I can say that one hard. So this has been widely used to explain the efficiency of power consumption within a data center. I was told there would be no math, but the basics are that it's a one-based coefficient, so it's you're trying to get down to 1.0, and what it shows is effectively the amount of power that's consumed in total by the data center divided by the power that goes to running the IT workload. So effectively, if 100% of the power in the data center was consumed by the IT workload, that would be a 1.0 maximum of PUE. The numbers go up the more energy is consumed by the data center for the cooling and the power conversion and any other kind of auxiliary uses. You can throw lighting into that, those kind of things. So what we're seeing is that the number one is as you compare between data centers, the PUE can be affected by improvements that you make in some areas. And I'm sorry, I'm not going to be able to go into the detail of how that happens, but there are times where you can do the right things, move to more efficient implementations, and actually worsen your PUE. And so that's one of the issues that has to be dealt with. But we're also seeing that as folks have realized the best case scenarios, the best practices for data center design, most of that is moving to liquid cooling and other efficiencies, that we're kind of reaching an asymptote, a plateau or bottoming of PUE around 1.2. There will ways probably to continue to improve that, but we're starting to really get very, very small gains. But there's a lot of stuff that can still be improved upon. It just won't affect PUE. So that's what this work group is looking at is what's next. How can we further the drive for more efficiency, and obviously having metrics that show that to show that you're making progress and to be able to compare is how you can help drive that. So while PUE was looking at that data center level, it was assigning anything that was going to the compute infrastructure, meaning if it went to the rack, or to the rack of IT gear, that was considered an efficient use of power, as opposed to going to the chillers or the air handlers or the air conditioner units. That was considered the inefficient use. So, but we know that inside the IT gear, there are some categories of energy consumption that are not, that fall into that non-efficient use of power. Most of that, you can see this little chart here shows, colored in green, of course, is the computational. So that's the actual power being consumed by the workload. But then there are kind of three categories, and there's lots of little slivers in here too, but the three big buckets of non-IT power, that inefficient use of power, goes into thermal management, so that's typically fans. One of the ones that surprised me was the power conversion losses. I thought that we had gotten to platinum level high efficiency power supplies, and we have. But there's another category of power converters, the voltage converters or VDCs or VRMs, they go by a lot of different things. They have not received the same scrutiny that the silver box power supplies have over the decades. It turns out that when you have GPUs consuming kilowatts of power in those kind of orders of magnitude, if you're running all of their power sources are all running through DC-DC converters, times 1,000 watts times 80% efficiency instead of 95%, well, that suddenly becomes, hey, I just lost 150 watts of waste heat in that conversion. So there's an area that we really need to look at. So that's one of the other large areas. And then the last area is the idle power. So that's all the IT componentry, the processors, memory, and storage that are sitting at idle. They still consume power. There have been a lot of gains in this area, but this is still an area that we need to look at is what can we do as system designers to reduce the footprint at idle. And so I'm sorry. And so the idea now is to then take what was PUE and now take that to the IT level and call this, I think the name of it is the IUE, the IT utilization. And so this is now a zero-based coefficient to say take the total amount of power over the computational power, basically the green box divided by the total, which would be the dark blue box, and so you get a percent. So it's basically you're trying to drive that up to 100%, or 1.0 would be the peak. There's reasons for having those at different scales, and you can do multipliers and things. And I was told there would be no math. Measuring these things at load is part of the definition, is where we have to get to is determining how do you figure out what the idle power is. And it's important to have these things measured at various load percentages, because these inefficient uses of power are not linear, and they don't necessarily, and they're also not necessarily increasing as load increases. For instance, the power converters, the DC voltage regulators, can be more efficient at higher loads than they are at lower loads. So while the total power goes up, the wasted power in that inefficient conversions can actually decrease. Fan power is definitely nonlinear. As you get warmer and warmer and have to run the fans faster, running a fan twice as fast is going to consume more than twice the power. Lots of this kind of stuff. So it's important to measure these things at loads. You can't just take a static value and say, well, that's good enough. So. Which is what's going to drive us then into the next part of the talk, which will talk about, hey, well, how do you measure this? How do you actually retrieve this stuff? So before I get there, though, is that the summation of all this, and see there's sigmas on there. I was told there would be no math. But that is basically just you take all of the componentry, at, say, a rack level, you sum all that up, and you get the total power, and then the total IT power, the total fan and non-IT powers, and then you can do, this is basically, that becomes simple arithmetic then to do those divisions. So that's the metrics. That's defining what it is we'll be measuring. You then take that up, at the rack level. You can then take this up to the data center level, rack by rack by rack. and you keep that granularity, and we have those things reported, at that granularity. Now the data center operator has information they can use to make decisions about how to deploy workloads, where are areas in the data center that need attention, what is equipment that should be upgraded, et cetera, et cetera. So it's all trying to driving these decision-making processes, backing them with data. So having the data and having some consistent reporting of that is what this work group is all about. So now moving to the other work group, the power and telemetry work stream. So this group focuses on, okay, we've defined the metrics that we want. How do we get that extracted from the systems, so that it can be, consumed? So the group sets those recommendations. We've started at a very low bar. What I need from the systems to start with is I need, energy consumption from the wall. I would like to get some more details, especially some of the major subsystems like the CPUs, the GPUs, the power supplies, to know about the efficiencies, the input versus output. Those kind of things are important, but to start the bar low, if I can just get power measurements, or power and energy measurements from the units themselves, then we can start to build these models and start doing comparisons. There are some other details that go into these things. The way that trying to get some consistency on the units. Things like fans. Some folks are driven based on the speed of the fans. That can be a proxy for the power consumption, but it's not necessarily true. So helping to define these metrics, these data points, so that they can be so that we can get consistent data from across multiple vendors. That's the main drive of this work stream. So the way that we are doing that in the work stream is, and that's why I'm wearing my Redfish shirt. OCP and hardware management, which I'm also one of the co-leads of the hardware management project here at OCP. So this is why I'm here doing this. The way that we extract management data, or just any of this kind of telemetry from systems in OCP, is we've used the Redfish standard for remote systems management, and I'll talk about that a little bit here. So Redfish is an industry standard. It is a JSON-based HTTP RESTful interface. If you know anything about web programming, that should all make sense. Otherwise, don't worry about it. It's a common standard for us to extract data. Redfish defines explicitly every property that comes out, and what the value ranges and the units of measure should be. So Redfish defines how you report power consumption, how you report energy, and other things like make, model, serial number, all the kind of stuff that we need to correlate all this data together. It's all in the standard. So what we do in the work stream in sustainability then is to define what's called an interoperability profile, which is a fancy way of saying a checklist of requirements. So Redfish defines several thousand parameters that can come from a piece of gear. We care about 15 of those. So we put requirements on those saying, as a managed device that meets the sustainability goals, you have to report the following things. And let's see, I've got that on the next slide. So that is done in a document. It is then, and that document's a machine-readable JSON file. Those set of requirements can then be used in conjunction with an open source validator that you can point to a working product and say, does that product report the data in all the required parameters, and it will give you a thumbs up, thumbs down. Does that product meet that? So it's a whole ecosystem here for us to say, okay, if your product wants to meet the OCP sustainability goals, you have to report this type of data, and you have to report it in this manner. So that's what that structure allows for. And there's links here for all that stuff, and we can certainly get you connected into where those things are. This is all publicly available. It's on GitHub. Everybody can look at it and take a look. You don't have to know anything about the underlying structures, because there's a human readable documentation that gets generated as part of all this stuff. So the profile itself, we cover three categories of information. And again, it's all trying to get these metrics, but there's a lot of ancillary or metadata that has to be there for folks to be able to correlate this to something useful for actually measuring this stuff. So the first is, and this is kind of this is almost obvious, but it has to be there. You have to have product identification. If I don't know what it is I'm talking to in terms of vendor, model number, SKU, basic configuration details, well then I can't do an oranges to oranges comparison because if I don't know what those things are, then I can't know if that's good or bad, right? So that's the first set of data. The second set is physical location. So where in the world we reside is going to be what you're going to use for your carbon coefficient, the carbon coefficient. I'm going to get that term wrong, but how much of your electricity is coming from from green sources. So knowing where that device is one way to help locate it, based on the geographic details. And there's lots of other caveats to that, but this is a step in that direction. And then the last and the most important part of this is energy and power consumption, and we would like to see both. Most products in the IT industry have reported power, which is like the instantaneous, actual power consumption. I talk about this as in terms of the speedometer and the odometer. The speedometer tells you, how fast I'm going. That's my power meter. That's what's been traditionally available because that was used for gauging, am I going to trip a breaker because the consumption has gone up. The issue with measuring power is that I have to keep watching it because looked at any of the IT gear knows that it's extremely dynamic. I can go from a kilowatt of consumption on a server down to 150 watts, in the matter of seconds, all depending on what the workload is doing. So trying to get an accurate count of that is difficult. So we really want folks to report energy consumption, which is your odometer or like your power meter, because that's a running count of what is being consumed. So I can come back to you at whatever granularity I care about, be that 5 minutes or an hour or a day, and say, okay, you've consumed this much energy over that period of time. And if I don't need the details at 5-second intervals, I don't have to gather all that data. I can just come and ask you at the end. So those are the three areas that the profile puts in, and that starts at some base level requirements, and we're going to move then in the future to put more granularity into that, put requirements on reporting fan power and DC converter componentry, ins and outs, to be able to pull more of those efficiency pieces that again tie in with the other the requirements of the other work stream we're creating. So that's it. I'm out of time, and thank you for your attention. Probably have time for one question while somebody moves to the next one. Oh, which is our panel. Yeah. What does the I stand for? It's for IT.
Okay.
So it's there's no good way to say it's the compute gear, right? So I kind of try to define that as it's basically if the energy is being consumed in the processing or movement of or storage of data, that goes into that bucket. And that's trying to cover both all three of the legs. The compute pieces, the storage, and the networking componentry, because all that is about moving and processing of data. Everything else, be that a fan, a blinky light, a front panel display, losses and conversions, that would be considered, wasted power. Hate to call it that, but that's what it is.
Thank you.
All right, and then we'll move on. We have another panel. I guess I get to sit down.